So continuing on with our example, we're now up to the second cut. Okay, so just going to display to you the original diagram we had over here. The second cut is from where this moment starts up to just before the hinge. The interval is from 1.5 meters out to 3 meters, but we have to include the first cut as well when we draw the whole diagram. Okay, so just showing you cut 2 now. Once again, the extremities are from 1.5 to 3. We're cutting from the left. The following is our diagram for this cut. So we firstly do sum of forces about the x direction is equal to 0. N is the only horizontal, so it equals to 0 immediately. Sum of forces in the y direction is equal to 0. Okay, so we have minus 10 minus v equals to 0. So this gives us a shear force of negative 10 kilonewtons. Next we have the sum of moments about point B to equal 0. So over here, right, so we have 10 times x minus 30 plus m. Now what is this? So we have 10 times x, we have this force over here causing an anti-clockwise moment, which is positive and has a lever arm of x away from point B, so it's 10x, right? Then we have minus 30 because of this clockwise moment here, then plus m because of this moment here. And rearranging this, we find that m is equal to 30 minus 10x. Okay, now since it's a polynomial of degree 1, it's a linear distribution, so we need to substitute the extremities to work out the magnitudes of the moments at different locations. So once again, our extremities are 1.5 out to 3. So when x is equal to 1.5, moment is equal to 15 kilonewton meters, and when x is equal to 3, m is equal to 0 kilonewton meters. Okay, as you can see over here. So that's our second cut. Now our third cut is exactly like our second cut, except now the hinge comes into place. But technically there's no additions of external forces. The only thing we're adding is the hinge. Okay, so essentially if we're adding the hinge and no other external forces, we're going to end up with the same equations as the previous cut, except now we're going to have different extremities. Because if I show you the original diagram, the third cut is from the hinge, okay, to just before this point load, whereas the second cut was from the moment to the hinge, just before the hinge. Now the only thing we added in the third cut was the hinge and no external forces. Okay, this is why we're only gonna have we're gonna have the same equations as the previous cut, except we have different extremities, which are 3 meters to 4.5 meters. Okay, so this means our axial force is once again 0 kilonewtons. Our shear force is once again minus 10 kilonewtons. Okay, and once again the equation of our moment is exactly the same, 30 minus 10x. Okay, so the only different thing is we're substituting a different interval. Okay, so when x is equal to 3, and this is exactly at the hinge, because if you look at the original diagram over here, the hinge is exactly 3 meters. Okay, it's in the middle. So at x is equal to 3 meters, m is equal to 0 kilonewton meters. And remember guys, I said in the beginning, what is a hinge? A hinge is a point that is free to rotate. There's no rotational restraint, so the moment about a hinge is 0. And guess what? It is indeed 0 kilonewton meters. Okay, and at x is equal to 4.5, our moment is negative 15 kilonewton meters. Okay, so that was our third cut. Now we do our fourth cut. Once again, our fourth cut is, if we're cutting from the left, our fourth cut is from 10 kilonewtons, okay, to just before the fixed support. Okay, and the extremities are 4.5 to 6 meters because we're cutting from the left. However, when we draw the diagram, we have to include 1, 2, and 3, the 3 cuts before it. So cut 4, extremities from 4.5 to 6. The following is our cut. Okay, we have, this is our cut here, cut 4, with our internal reaction sign convention once again. So sum of forces about the x direction is equal to 0. N was equal to 0 kilonewtons. Then we have sum of forces in the y direction, so the vertical is equal to 0. So we have minus 10, which is over here, minus 10, plus 10, because this 10 is pointing upwards, minus v, because v is pointing down, is equal to 0. so V is equal to 0 kilonewtons. So in the fourth cut we have no shear force because it equals to 0 kilonewtons. Okay, now we find our moment since we've worked out axial and shear already. So sum of moments about point B is equal to 0. Once again, point B is at the internal actions. So we have M, which is this moment over here, minus 30, which is the clockwise moment over here, plus 10 times X. What is 10 times X? Okay, so since this is point B over here, this force over here, 10, has a lever arm of X about point B, and it's an anti-clockwise moment, so it's positive. Okay, minus 10 into X minus 4.5. Now what is this? So we have a minus because the following point load creates a clockwise moment about point B, and the lever arm is the distance from here to here. And since the whole thing is X and from here to here is 4.5 meters, the following interval is X minus 4.5 meters. So we're doing minus 10 times X minus 4.5 is equal to 0. So this is everything for our moment. We find that the moment equation is equal to 30 minus 10x plus 10 into x minus 4.5. Okay, so once again it's a function of x. We have to substitute our extremities. When x is equal to 4.5 meters, the moment is minus 15 kilonewton meters, and when x is equal to 6, our moment is again minus 15 kilonewton meters. So we've worked out our internal actions at each cut. Now we can draw in the diagrams. Okay, so this is our original diagram here. We found that n was equal to 0 at every single cut, so here, 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 and here were all 0, so our axial force diagram is just 0 kilonewtons. For our shear force diagram, we found that in cut 1, 2, and 3, we had a shear force of minus 10 kilonewtons, and in the fourth cut, we had no shear force, so there's nothing to be drawn in, okay? Or you can write in 0 kilonewtons for the fourth cut, okay? Now, the bending moment diagram. In the first cut, we had a linear distribution since it was a function of x. Sorry, it was a polynomial degree 1, so it's a linear distribution. So in the first cut, the moment was from 0 to minus 15 kilonewton meters. Okay, in the second cut, we had once again a linear distribution from 15 kilonewton meters down to 0, which is at the hinge. The third cut, we started the hinge once again. We have a moment which equals to 0, and it went down to minus 15. And in our fourth cut, we had a constant moment of minus 15 kilonewton meters, so it's drawn as a constant, as you can see over here. So that's another example of bending moments, shear force, and axial force diagrams. The main point I wanted to show you from this video is how to deal with moments about hinges. So just understand the two rules that I'll show you here once again quickly before I end this video. Moments from either side of the structure about a hinge is equal to 0, or the total moments about a hinge is equal to 0. And as you can see over here, at this point we have our hinge and the moment was 0 kilonewton meters. So thank you for listening.